Some have suggested that we now live in an algorithmic culture or an algorithmic society. That term algorithm is certainly very old. I mean, the idea of an algorithm goes back as long as mathematics has been around. The actual word algorithm is almost as old. It goes back at least now 1,000 years. But it's come into much more common usage. I mean, if you asked someone on the street what's an algorithm 15 or 20 years ago, they would have no idea. Actually, if you ask them today, it's probably still the case. There was this set of ads for ask.com that said, what is the algorithm? Ask the algorithm. I think a lot of people have become more familiar with the idea of an algorithm around search engines, and that's appropriate. But let's talk a little bit about what an algorithm is and why that might have more effect on society now than it has in the past. So what's an algorithm? An algorithm is just a way of solving a problem or a way of processing information. So in that, it's fairly simple. It's not unlike a program. So people may not feel as strange about the idea of a program as they do about an algorithm. They're very, very similar in terms of what they are intended to do. Programs are implementations of algorithms in many cases. But it's kind of a plan, a way of solving a set of problems or working through problems of processing. So when I started in college, the computer science programs were entirely algorithms and data structures. In fact, in the computer science program at the school where it was actually information and computer science, at the school where I did my undergraduate, you didn't even really learn real programming languages. Yeah, you learned a little bit of assembly and you learned a little bit of Pascal, but you didn't learn programming languages that would get you programming jobs, because that was seen as something you'd learn in a tech school. Computer scientists were supposed to study math and algorithms and data structures. So we needed to know how to more efficiently solve fairly complicated problems, not necessarily how to code those into a program. So the ideas are kind of what are the structure of what creates an actual program. So in an introductory computer science class, even today, you probably start to learn some algorithms that are around searching or sorting. One of the traditional ideas that you get exposed to is the simplest version of how to sort a list of things, and that's called a bubble sort. And, if I ask you how do you alphabetize something, it's something you learned probably to do in kindergarten or first grade. You know what it is. You know what the end state's supposed to be. Everything's supposed to be in alphabetical order. But the actual process of telling me how to do that, of how to take books on a shelf and organize them in alphabetical order, that might be a little bit more difficult to describe. It's even more difficult when you have to describe it to a computer. One of the ways that you can do that is to go through the entire list of items, and if they are out of order, flip them. So go to the first two items in a group. If they're out of order, flip them. Go to the next two items. If they're out of order, flip them. Go through the entire list and do that. Is it in alphabetical order? No, of course not. Well, it might be, but it probably isn't. So then you go through most of the list again, and you flip them again. And then you keep going through this over and over again, almost as many times as there are items in the list. That's not quite true, but and in the end, you end up with an alphabetized list. So this is an algorithm. It's called the bubble sort algorithm. Probably in that same class, you'll learn an improved version of this, a faster way to do this. There's a number of different ways of sorting through this information. There's whole books of algorithms on how to efficiently sort different kinds of lists of things. You might, in that first class, encounter something called a quick sort algorithm or some other algorithms that are designed to be slightly more efficient in making that kind of sorting process. The other kind of things it might do is categorize, right? If you have some information coming in, what kind of information is this? Can you sort this in various ways? But honestly, once you go through, maybe there's three different kinds of large groups of algorithms. There's searching, there's sorting, and there's categorizing, and they're all very closely related. If you think about what computers do, there's other things that they do. They control processes, they have interface controls, a whole bunch of, they allow you to store information. But the main kind of processing they have to do are those three tasks. They have to sort things, search through them, or categorize them in some sense so that they know where to put them, right? And they're all very closely related. They're certainly related to the area in which algorithms have proven to be the most the most profitable, the most influential, and that is search algorithms. So search is a problem of categorization. It's not actually a problem of search, which is kind of strange, because what you have to do is you already have an index. So actually finding the records related to what you're searching for is not that difficult. In fact, you can say, an actual index of the web would just say, give me all of the hits that have my word on the page. And frankly, that's what the earliest search engines did, and that's very useless to what you're doing, what you're trying to look for. And so the actual algorithms are much more complicated, and they try to search for and find and surface the best solutions to your problem. So they don't want to just find everything. They want to find the closest matches, the things that are nearest to what you're actually looking for. And we can talk about that in a lot of depth, but those algorithms can draw on all kinds of different pieces of information to help to determine what's going on there. Particularly over the last decade, although certainly over the last several decades, people have been trying to figure out algorithms that do all sorts of things well. Web search has been a great sort of boon for folks who are interested in questions of search and intelligence more broadly. The folks who started Google were not primarily interested in search engines. The web was just something they were working with. The idea was to be able to make practicable forms of artificial intelligence, forms of decision making by a computer, and sorting and finding the best decisions. If you think about intelligence, in some ways it's just that, right? If you wanted to make an artificial intelligence, the ability to find the best solution to a problem is pretty much the definition of what artificial intelligence would look for. But in artificial intelligence, there were a certain class of problems that were especially difficult, and that hasn't changed. So if I'm a human being, if I'm a lizard, but also if I'm a human being, if I walk into a room, or scurry into a room, I guess if I'm a lizard, I can look around and I can quickly come to terms with what the objects in the room are, right? We have this very low-level processing in our brain that separate all of these lines that are coming in from our eyes. The eye itself actually determines where some lines and patterns are, but those go into your brain, and very quickly your brain kind of automatically can sort the room into objects. And it's not just humans that can do that. It's fairly low-level, things with very small brains can still use if they have eyes, if they can use visual information or other sense information, aural information or scent information, and they can very quickly sort through a mess of stuff that's all right there. And that's something that for a long time it was thought that really only humans and animals could do that very well. There was some push, and this goes all the way back to the earliest days of electronic computing, this idea that you could somehow simulate neural networks and therefore replicate the kinds of things that happen in a brain. And people were thinking about questions around this, as I said, straight back into the 1940s, but certainly during the 1970s and 1980s, there was a lot of playing around with this idea of creating neural networks, trying to replicate this ability to recognize things in a noisy kind of atmosphere, draw out what's interesting within a large collection of things. Again, that might sound slightly familiar. It's a little bit about what you have to do when you're trying to find things on the web. It's this very unvariegated, very sort of messy combination of things with lots of different points of data and lots of different information sorted in different ways. And so how do you extract from that the thing that's really useful? And that's similar to what you have to do when you go into a room and figure out what's there. When you look at an image and classify it, you say, oh, these are the objects in that image. Or when you look at a person, you say, I know who that person is. It's X. All of those are processes of kind of taking complicated information, like a face can, you move it just a little bit and it makes it much harder to classify it. So taking these complicated pieces of information and somehow sorting them back to their best match. And as I said, traditionally that's been something that humans have done really well. That's why we have CAPTCHAs, right? Those are those things where you have to prove that you're not a robot. This effort to prove that you're not a robot. And those have had to, if you haven't noticed, those have had to evolve over time because computers are getting much better at figuring those out. But that's why CAPTCHAs exist, right? They're a good way of sorting the person who's entering something into a form between a human and a computer, because again, it's thought that CAPTCHAs are something that humans are especially good at doing. There's a whole side note here that we could talk about how people have gotten around CAPTCHAs, but generally speaking, it's been meant to be a filter between humans and non-humans. In fact, Amazon has this project called Mechanical Turk, which you may or may not be familiar with, where Turkers, the people that work for Mechanical Turk, are given very small projects to do, like things that should only take a few seconds to do. And some of those projects initially were things like, tell me the objects in this picture. And this was a way that people could design computer systems and then outsource these very difficult tasks that are very easy for humans to do. They could pay someone 5 cents a shot to say, read this word to me that's in cursive, because as a computer, I can't quite read it. And it was this very funny thing, because we'd always thought of like humans being augmented by computers, but Mechanical Turk's just the opposite. It's smart computers that are being augmented by human intelligence for these little, trivial things like recognizing faces or objects in a picture that computers still couldn't do. As it turns out, one of the things they were doing during this process was training neural networks, computer neural networks, to be able to do what humans were doing. So alongside with kind of simple search algorithms are algorithms that are usually classified as machine learning. Machine learning means a whole bunch of different things to a whole bunch of different people, but it generally means classifiers. The main area in here is things that can classify information or data in various ways. So they can do things like take a picture and say what's in it, or take a photograph and say what things are in there, or take an image of a person and say which person it is. These are classification tasks, and machine learning should be able to do that. And machine learning improved by leaps and bounds, and especially over the last 5 to 10 years, they've moved from machine learning to a particular kind of machine learning, and it's actually a subset of algorithms in machine learning called deep learning. The only real difference between machine learning and deep learning is that for machine learning, you had to really help the algorithm to know what to look for. So you didn't have to classify the image for them, but you had to say, here are some clues that you can look for, some features, and that's the facial recognition is a great example of this. So when you're looking at a face like mine, how do you tell the computer to tell one face from another? And you could just say, well, I don't know, take the average color of the screen and figure out what it matches. This is a really bad way of matching people, because things like lighting and direction, all kinds of things mess with that. You could say, okay, how, the physiognomy, how can we measure the face? And one way you could do that is you identify the eyes, which aren't hard because they're usually round, and they usually have a dark pupil with an iris around. So you can, finding the eyes isn't that hard. And then from there you can estimate where the tip of the nose is, and you have this triangle, and then maybe you can see where the face is and how far the mouth goes out and where the chin is. Now, generally it's only going to work when I'm face on, but you can identify these elements, and then from there you have kind of a set of measurements, and you can match that with measurements that you have on file to see if the person is there. And so you can create, once you've told the computer how to find the elements of the face, then you can tell them, you can kind of train it to be able to compare those measurements with what you have on file and come up with a good guess as to who the person is that you're looking at. And that still is a lot of the ways in which facial recognition works. Deep learning takes a step beyond that and says, we're not going to tell you what features to look for. Here's a bunch of mess of data. Here's just a pure image. You figure it out. And it does that in some fairly complicated ways. In many cases, you can't really tell how it's decided to figure this out. This is the next big step in deep learning, because they're giving us answers, but we don't necessarily know how they've thought about this. Because the algorithms often arrive at answers in a way that is useful to us because it can classify these things, but it may not actually follow the same pathways to get there. And it's not just recognizing faces. You can throw all kinds of data at this and help to classify it. So what are some other things you might want to classify? A really important thing to classify is whether someone is having a heart attack or not. When they come into the ER, there are a number of ways people have done this. Traditionally, doctors are taught some signs that might indicate a heart attack. It turns out that they're really bad at remembering that on the fly. And so they've moved to checklists where they can actually, in the same way that a pilot might, they have a couple of things that they're supposed to check one by one, and then they can add them up. And if they've got these things, then yes, this is a likely heart attack. But it turns out that computers are really good at finding some of these things that humans can't identify well. And it's not really clear how they're learning to do this. They're, for this creepy Skynet piece, in some cases they're doing better at identifying and classifying things that humans are. And we can still work with them. There's augmentation. In fact, there's this project with Mayo Clinic and ASU together, researchers, and they everyone has to get colonoscopies eventually, right? And the problem is that people who read these colonoscopies, it's just not that thrilling. It's not exciting to be looking at the insides of human bowels all day. And so if they get distracted, if it's getting close to lunch, they might miss something. It's really hard to be kind of concentrating on these images and finding things. And so they came up with this project that actually identifies not polyps necessarily, not things that are necessarily bad, but targets. They kind of say, hey, take a look at this. This is probably important for you to look at for the radiologist or the person who's reading the scan. And so those kind of things, it turns out that they're starting to do better. The obvious case of this, although recent evidence might be against this, is that, this is why people have this feeling that even though autonomous cars may not be as good as human drivers are right now, they're probably not as good as the best human driver is. It's still an open question as to whether the average autonomous vehicle right now is a safer driver than the average human driver on the road. Google makes the claim that it is. They say that, their cars have driven now several million miles without any accidents that were, their fault, that it wasn't another car running into them. So it may be that it's already there, but there's a lot of promise here that autonomous vehicles will be safer drivers than humans are. This is one of those tasks that, even 10 years ago, it was assumed that this would be something that was a very difficult thing to teach computers to do. It's a complicated task with lots of various information that, really weird things that can happen to you while you're driving, lots of kind of strange things that can happen. You might actually train for I'm sure when you learn to drive, you saw a video with the bouncing ball and how to think about if there's a bouncing ball, a kid's going to dash after that. That's kind of one of the obvious ones, but there's all of this stuff that comes just from experience. People become much better drivers all the way into their 60s. They're much less likely to get in an accident just because they gain that experience. What happens when computers are 100 times better at you than that? Obviously, it would be right. Right now people are saying, oh, I don't know if I want AVs on the road or not. But the question then will be, what kind of idiot, what kind of real jerk decides to drive his own car when there is such a risk when there's such a higher risk that will lead to an accident than if you just let the car drive itself? That question, early on, that question will be answered by the people who are those jerks are going to have to pay much, much higher insurance rates. If you decide to drive your own car rather than having it drive itself, your insurance rates are going to go through the roof, right? Because insurance companies will have to pay out much more on the people that are self-drivers. But eventually you're going to have these questions coming up a lot. What happens when the doctor ignores the advice of a deep learning AI that says someone's having a heart attack or someone isn't having a heart attack, and either wastes money or kills someone because they're trusting their own human instincts over the machine? I think cases like this are going to rise over and over again. So that's one piece, which is already in certain small domains, we're seeing the incursion of these, especially deep learning algorithms, on human decision making. And it seems that machines are better at some of these things than we are. That point when computers were better at playing chess was an important one, I guess, because it was a complicated human endeavor. But computers play chess in a different way than humans do. It turns out with heavy processing that they're better at that, right? But it's not necessarily that's not necessarily the case across the board in all domains. It was a very specific domain. Now we have a whole bunch of domains in which computers are starting to get better than humans are at complicated kinds of problem-solving issues. So one of the questions is what happens when those multiply, when deep learning is applicable to a really wide range of problems. And we're going to find out just how wide a range of problems this particular set of algorithms is good at solving. Because rather than offering kind of, Google doesn't just do, instead of Google and other companies, rather than just offering solutions within these narrow domains, are offering sort of deep learning as a service. So they can kind of, if you want to apply this to, if you just want to add deep learning, it's becoming easier to do that because you can kind of plug in cloud-based systems that will do this very heavy crunching and come up with solutions. And then you can play with that and see what domains you can apply this to. And so this is going to accelerate over the next decade as more and more people are figuring out how to use these systems and how to effectively apply them to new problems. I doubt it's going to be every set of problems. I don't think that we're going to find in the next 10 years that computers can do everything better than humans can. But I think we're going to find a whole bunch of areas in which they can do that, and that's going to lead to some interesting stuff. The other piece to add into this is the big data question, especially on the social side, that there's now huge amounts of data that humans just aren't very good at crunching because there's just too much of it to include in at least an instinctual model. So we aren't going to make the same connections that computers can with these large collections of data. And already, again, this is happening. There's a program that's funded through DARPA that looks and sees that can predict when there's going to be a riot or public demonstration. It's right now applied to South America, and it can predict it with really uncanny accuracy. Now, I don't know how accurate that will be in the long run or whether it can be sort of applied very broadly. But the idea that a day ahead of time, if there's going to be civil unrest in a city is amazing. And it does this through really a ridiculously large collection of data. And there's no reason that collection couldn't be larger. So it's drawing on things like news, on search data, on reservations at restaurants, just this really wide range of things. And as a human, if I'm going to take these and try to weight these into a solution, it's kind of like people who try to figure out who's going to win a horse race, right? They didn't eat on, he does really badly on Tuesdays historically. There's only so much you can do intuitively with this. And it seems that, strangely, computers are getting much better at intuition, at finding these kind of connections that humans can never really find. And in many cases, the computer also can't explain to you how it reached that. It's effectively correct, but it can't explain to you how it reached that. And that's not a problem necessarily. If it's saving lives, you just have to go with it. But it turns out that sometimes they're doing this in a way that is kind of obviously racist, for example. And so if it's making decisions on mortgages, and it can't tell you why you haven't gotten the mortgage, and it can't tell anyone why you haven't gotten the mortgage, and yet people are trusting it, that leads to some very strange policy questions. So, are we living in an algorithmic society? No, we're not. Search engines do matter. They have a huge impact on marketing budgets. They have an impact on what we find. They now have an impact, obviously, on how we encounter news. These are algorithms that adjust your feed. So obviously the algorithms that adjust Facebook's feed, this is why they're trying to fix them right now, absolutely have an effect on things like national elections. So yes, the influence is broad. I don't think it's overwhelming yet. I think that when we talk about an algorithmic society, we're talking about the potential, and that potential, I think, is pretty high. And I think that if there was one thing that you wanted to be looking at, it's taking a critical look at how this new set of algorithms and sources of data, how this combination has the potential, at least, to have very rapid and very extreme effects on our social organization.